1, go.
Good afternoon, everyone. My team and I will be presenting the Scenarios Week 2 iMechE Design Challenge 2021, where we will be presenting an updated virtual design of our device following the feedback from Scenario 1. Due to COVID-19 restrictions, it will not be possible to build and physically test our device, so instead, we will be virtually competing by using the simulations tool created by the iMechE. Thanks to this app, we will be running some tests to improve our model.
After receiving constructive comments in Scenario Week 1, we had to make some changes to our initial design to make it better. An important design change was the use of a button switch, which travels much less distance before turning the car off. Another design improvement on the vehicle was the wheels. These changes will be detailed by my teammate later. For this week, our main goal was maximizing speed and minimizing energy use. Apart from the changes in the wheels, we also made weight savings in the chassis of the car to make it faster.
The testing part of the challenge was carried out using an application that simulates the procedure of the car completing the truck using data that our team derived for our final design. It then created the simulation video so that we could have an idea of the actual race and to check if our car failed to stop at the target. After that, data output was calculated, such as the velocity gradient, energy usage, and time required to complete the truck. We then took this output, created an Excel sheet, and came up with two graphs. One graph of velocity against time and another of the energy usage against time. This procedure was repeated many times, changing different input parameters.
After running a few simulations with different springs and different stiffnesses, we quickly realized that the total energy and velocity of the vehicle was always very similar. We also realized that the bottom is always pressed against the wall and the vehicle always goes back to its starting position. So we decided to use a spring with a stiffness of 277 newtons per meter.
To choose the appropriate wheel size, we went back to the basics of circular motion. From this equation, we deduced that an increase in the wheel's diameter will also increase our linear speed, given our motor angular velocity. Hence, we chose to increase it by 4 centimeters. Since our wheels are thin and light, made from 3D printed plastic, the total mass would not be significantly affected, and hence the results. Finally, to avoid slipping of our car, we added a rubber band around each wheel to increase the coefficient of friction.
We wanted to change the motor to be able to increase speed without changing the gear ratio. We tested motors with no-load speeds of up to 20 to 100 RPM, and although this gave a high and acceptable speed, the stall torque for this component was too high and increased the power output quite drastically. We also had to consider the cost of the motor when researching online, which limited the ones we could use. So we ended up going with a model which has a no-load speed of 1800 RPM and a stall torque of 0.005 Newton meters, resulting in a cruise speed of 0.88 meters per second.
Creating the bill of materials was an interesting challenge, which proved that our initial ideas were not 100% achievable in terms of price and manufacturing. It was also challenging to find cheap parts that are reliable enough for our vehicle and use materials as light as possible.
To conclude, although the goal of this week's scenario was different to the last, we adapted well and changed our approach by focusing on the use of the simulation to test the effect of different variables. We managed to make changes to increase the speed and therefore decrease the runtime, while still managing to improve our general vehicle design using the advice we were given in the last review. Our final design gives us a runtime of 5.98 seconds, as you can see here, with a total energy usage of 1,474 joules, which is the area under this graph. Thank you.